Alrighty, folks. Well, it looks like my camera is not working today, so I guess the next couple videos are going to be missing the camera for this portion. But let's just do a quick review of our definitions. So when you bisect something, you're cutting it into two congruent halves. So angle ABD is congruent to angle CBD. That way we can make a claim that says two angles are congruent. Perpendicular lines. They are two lines that intersect and form right angles. The fancy thing we know is that all right angles are 90 degrees. Now, off to the side, answer the question that pops up. Cool. Hopefully you answered that 90 is equal to 90. So, if you have two 90-degree angles, they are always going to be congruent. This is by the right angle theorem. The linear pair theorem is something that we're going to be skipping for a little while at least. And same with the congruent supplements theorem. Reflexive postulate. Have you ever looked in the mirror and said, hey, I look a lot like myself? Well, that's what the reflexive postulate says. Anything is congruent to itself. So it might look a little redundant, but BD is congruent to BD. It's the same line, so it has to be congruent to itself. Something that you're going to hear countless times this year is that all vertical angles are congruent. So angle 1 is across from angle 2, so they are always going to be congruent. We're going to be skipping the addition postulates, but we are going to be talking about midpoints again. These are points in the middle of a line segment. So if you are given that S is the midpoint of line segment RT, one conclusion you can make is that from R to S is the same length as S to T. RS is congruent to ST. And that's going to be the same thing with the definition of a segment bisector, because CM is congruent to MD if AM bisects the segment CD. Here is a list that I would like you to copy down. So off to the side, I'm going to make you pause the video and copy down all of the reasons why it's possible to get congruent line segments. And then I'm going to scroll down and you're going to copy down this list of all of the reasons why angles might be congruent. All right, so first thing we're going to talk about is vertical angles. As you guys know, all vertical angles are congruent. We covered that last unit. So what we can say when we look at a diagram is angle AEB is congruent to angle CED. So I'm going to take that and I'm going to put that into my statements column, because that is a statement that angle AEB is congruent to angle CED. Anytime we make a statement about something, we have to back up why it's true. We have to give an explanation. Every statement needs a reason. So the reason why AEB is congruent to CED is because they're vertical angles, and all vertical angles are congruent. So we're going to take that reason and put it into our chart and say all vertical angles are congruent. If you know a symbol, you're more than welcome to use it in your chart. So let's take a look at another shape property that we can put into our proofs. Next up is what we call the reflexive property. This is something a little bit new to this unit, where we say that the reflexive property is something that is congruent to itself. So here's two different diagrams. First up, we have line segment AD. That is a common side between the triangle on the left and a triangle on the right. So when we look for reflexive, we're looking for a common side or a common angle. AD is on both the triangle on the left and the triangle on the right. So I'm going to hop on over to my T-chart and put down AD is congruent to AD. And I'm not going to forget the bars on top without the arrows means that they're line segments. Every statement needs a reason. This is the reflexive property. You are more than welcome to shorten property down to prop, just because Let's make your lives a little bit easier. Next, if I hop on over to this other diagram, I have two overlapping triangles. Let me get some more colors involved. We've got pink for triangle FHE, and we've got orange for triangle GEI. If you highlight these two triangles, you'll see that they both have angle E up at the top corner in common. What we can do is say that angle E is congruent to angle E by the reflexive property as well. Every statement needs a reason. I'm going to say it about 50 more times during this video. So anytime you make a claim, you got to back it up. So let's take a couple more examples that we have to take a look at. This time, we're going to be talking about segment bisectors. We already know what they are. A segment bisector is when you are bisecting a line segment. You're cutting a line segment, just a point-to-point connected. So in this case, CB is being bisected into two congruent halves by AD. Up top, we have this section where we call it the given. This is some given information to you that helps you answer the question. It's just like some given information in a logic puzzle. So we've got AD is bisecting CB. What this tells us is that when we mark our diagram, AD is cutting CB into two congruent halves. So CD has to be congruent to DB. When we know something, let's write it into our proof. CD is congruent to DB. Since every statement needs a reason, let's provide the reason. We are using the definition of a segment bisector. We defined a segment bisector as something that cuts in half. So what we write into our proof is definition, or DEF for short. DEF seg bisector is what I write in. That's one way you can shorten it and save yourself a little bit of work. So let's move on to angle bisectors. So this time we have an angle bisector. A line segment bisects an angle. Think about it. Grammar says that one is being cut in half. So AD is the actor. It is acting on the angle. AD is bisecting angle CAB. Where AD is cutting angle CAB into two congruent halves. So those two congruent halves are up top. One way you can label them to make your lives a little bit easier is throw some numbers in your diagram. So I'm going to number these angles 1 and 2. So when I write it into my T-chart, I can say that angle 1 is congruent to angle 2 by the definition of an angle bisector. And there you have it. Let's keep on rolling. All right, we have two triangles now, AED and BEC. We are given that E is a midpoint of AC. Now, we all know a midpoint is the point in the middle. So it's creating two congruent halves. So if E is the midpoint of AC, we can mark AE congruent to EC. So we claim that AE is congruent to CE, and the reason why is by the definition of a midpoint. Two things are probably popping into your mind right now. Mr. Carroll, why can't we say the same thing about B, E, and ED? Well, here's the issue. E, we are told, is only a midpoint of AC. We are not told anything about BD. So you cannot make a claim unless you have the information to back it up. The other thing you're probably thinking right now is, wait, couldn't I say definition of segment bisector? No, you cannot say definition of segment bisector simply because we're not given the word bisect in the given. We are given a midpoint. So first things first, you gotta use the information you're given. You cannot make up your own information, or else you're just making your life a lot harder and not actually answering the question. So let's keep on rolling. We got a bunch more examples to look through. Perpendicular lines. That's what this little upside down T in between two line segments represents. It represents that the two line segments are perpendicular. The definition of perpendicular says that we get some right angles. So if AD is perpendicular to CB, I'm going to draw in a box right there. And if it's perpendicular, we can draw a box on both sides of that line. To make my life a little bit easier, I'm going to number those angles 1 and 2. Here's the statement that I'm going to claim. The claim is that I know perpendicular lines form right angles. So let's say it. Angle 1 and angle 2 are right angles. The definition we use to get there is the definition of perpendicular. Now, luckily, we actually know one more thing about perpendicular lines and right angles. All right angles are equal to 90 degrees. Would you agree that 90 degrees and 90 degrees are exactly the same? So those two angles are actually exactly the same size, which means that they're congruent. So I'm going to write down one more step. This is important. Perpendicular lines take 2 steps. Step 1, say that they're right angles by the definition of perpendicular. Step 2, angle 1 is congruent to angle 2 by the right angle theorem. And that's all there is to it. You just got a pair of angles congruent from some perpendicular lines. Let's keep rolling. Next up, perpendicular oftentimes goes with parallel, and that's what these railroad tracks in between two line segments means. Railroad tracks, think parallel. What am I talking about? Perpendicular, T, parallel is the railroad tracks. AB is parallel to CD. Now sometimes these can be hard to see in your diagrams. So what I recommend you do is you take a fancy color and you highlight your two parallel lines, AB and CD. Oftentimes in a proof, if you're given parallel lines, there's actually a line connecting the two. So highlight that line too. And would you look at that? There's a Z in my shape. Or we have an angle at A, which I call number 1, and an angle at C, which I'm going to call number 2. Now, if you remember your vocab correctly, these are alternate interior angles, which are always congruent. So here's how we put it into our proof. Angle 1 is congruent to angle 2. The reason is a little bit longer, so listen and then write it down. If two parallel lines are cut by a transversal, the alternate interior angles are congruent. I'm going to write it down now. If two parallel lines are cut by a transversal, then the alternate interior angles are congruent. If two parallel lines are cut by a transversal, then the alternate interior angles are congruent. Transversal, all that means is a line connecting the two. That's that diagonal line in our diagram. It's long. It's challenging. Write it 10 times a day if you need to, but you're gonna need to know this reason. So, you're gonna have to memorize it. I'm sorry. Use symbols. Use shorter words. Alt, int, angle, use the symbol. Do what you have to do, but memorize this statement. It is going to be so important. It's going to be a really useful tool. Keep it in your tool belt, and it'll get you through the year. Let's keep on rolling. These next two are going to be easy to get confused. So it's really important we remember the definition of an isosceles triangle. Isosceles triangles are defined as having two congruent sides. So using those two congruent sides, in this case, AC is congruent to AB. We also know that they have two congruent angles. So using these sides, we go across from them, and we can see that angle C is going to be congruent to angle B. So let's write that into our proof. Angle C is congruent to angle B. The reason for this is called the isosceles triangle theorem. Using two congruent sides to get you two congruent angles. That's the definition of an isosceles triangle. Let's see how that's a little bit different from our next example. So you probably realize this looks really similar to what we just worked on. Only difference is this time we're given the two congruent angles. Angle C is congruent to angle B, and it's marked so in our diagram. Now that we have the angles, we can work our way in the opposite order to get us the sides and say, all right, well, if I know this triangle has two congruent angles, I know it has to have two congruent sides. So we mark them congruent in our diagram, and we hop on over and say AC better be congruent to AB. The reason this time, we switch the order. So think about your high top Converse shoes. You're doing some hip hop, hippy hoppy beats. Yep, we're going to do some of that and switch up the order. Say, it's the Converse isosceles triangle theorem. I can't sing. Yeah, I know. I used to be a music major. There's a reason why that didn't work out. I do math instead. Angles, getting you the sides, we switch the order. Converse isosceles triangle theorem. Let's keep rolling. We're almost to that finish line. Stay with me, and we're going to get through this. This time, our triangle is a little lopsided. It's looking a little less uneven. This time, though, we do have a median instead of something else that looks more like an isosceles triangle. We have a median AD of this triangle. As I talked about earlier, medians go from opposite corner to opposite midpoint. So AD makes D the midpoint of BC. So we can mark CD congruent to DB. Since we marked it, let's write it in and say CD is congruent to DB. The definition we use to make this claim is the definition of a median. All there is to it. It's not a segment bisector. It's not a midpoint. We were given a median, so we use the median. Always use what you're given. And let's keep on rolling. One more example, and then you're done for the day. You have made it to the finish line. This is the last one for the day, but please bear with me as it is a trickier one. So let's see what we can do. We're given altitude AD. We talked about altitudes earlier today, and a little bit yesterday, I believe. Altitudes. These are from a corner perpendicular to the opposite side. So right now we know AD is perpendicular to CB. Since they're perpendicular, let's say so in our proof. Step 1 says AD is perpendicular to CB. And that is because it is the definition of an altitude. Altitudes mean two lines are perpendicular. But we actually know something about perpendicular lines. We know perpendicular lines form right angles. So we've got two boxes we can put in. and label them 1 and 2. Angle 1 and angle 2 are right angles. And that is by the definition of perpendicular. Perpendicular lines form those right angles. So we got the right angles from the perpendicular lines, which we knew from the altitude. One more step. As we talked about earlier, 90 degrees is the same thing as 90 degrees. So we can say that those two angles are congruent. Angle 1 is congruent to angle 2 in this third step by the right angle theorem. That's what there is to it. I do want to take just a moment to draw your attention to this pattern that starts to emerge. This is going to happen time and again throughout all of our proofs this year, where we make a claim, something like this perpendicular, and that becomes our reason for the next step. We got the right angles, and that becomes our reason for the next step. We're starting to build an argument. We're starting to build a case, if you're thinking about it like a jury in a courtroom. We're building our case. We're gathering evidence and using it as we see fit. So, this pattern of down and to the right is almost always going to be helpful in some cases. So, that's all I've got for you. Please watch this video a second time if you can. Make sure you're taking notes. It's going to be helpful, especially as we move throughout this unit. And we're going to see how this starts to take shape starting in 2 days. So, I'll see you then. Bye.